Hey, welcome friends, and in this video I'll be talking about C-acylation versus O-acylation. So previously I made several videos on C-alkylation versus O-alkylation, and that is basically the effect of solvent, but this is some another point. It is not the effect of solvent, it is the inherent reactivity. So this is very important for you, so keep watching and let's start our today's topic. So as you can see, the problem is given this compound, this aromatic compound, and with this aromatic compound there is attached another ring, and the compound is treated with two conditions. First, triflic anhydride in presence of a weak base like triethylamine, and second condition, ozonolysis. So what will be the product? Now in the first step there is the concept of C-alkylation versus O-alkylation. So you are given a weak base triethylamine. So what it will do, it will take a proton from here. So if it takes a proton from here, you will get enolate. So this enolate you will get. I am not writing these OMe groups further because they have nothing to do with the reaction. So you will be getting this enolate. Okay. So now the real question comes of this question of this particular problem, that when you are reacting this enolate with this is triflic anhydride. This is the structure of triflic anhydride, and the acylation will occur on this particular enolate. Now from where the acylation will occur, that is either this O minus can attack here, or it can push its electron density and this C can attack here. Okay, so depending on the mode of the reaction you can get two products. So you can have either this OTF or you can have this. Okay, so these are the two possibilities. Now which you will get. So previously I made a video on C-alkylation versus O-alkylation, but there I told about the solvent effect, that changing the solvent you can shift the reaction from C-alkylation mode to O-alkylation mode, but in this case it is acylation, and whatever the solvent you are using, acylation always preferred on oxygen. Okay, so when you have a chance of C versus O acylation, the acylation will always take place on oxygen, because you can see between these two centers, this center and this center, it is hard center. Oxygen is more electronegative, so it is a hard center, whereas this is soft center. Carbon center is soft center. Now if we consider a normal alkyl halide like methyl iodide, so in this case the reacting side is the sigma star orbital, and this position, this methyl position, it is soft center. So in this case generally C alkylation is preferred, and if you change the solvent then you can shift the reaction to the O alkylation. But when you are using a acylating substrate, let's say in case of, in this case triplet is used, means triflic anhydride is used, but you can also given with acyl chloride or normal acid anhydride, this can also be given. So if these acylating substrates are given, you can see in this case the electrophilic center is this carbonyl group. So this is also a hard center because it has high positive charge density due to the presence of this two oxygen group, and in this case due to the presence of this CF3 group it is even more harder. So that means these two hard centers will prefer to react with one another, and you will get this OTF, that is O acylated product. So this is a very good reaction, because you should know that when you are when you will get C acylated product, and when you get O acylated product. Now normally so we have learned that normally O acylation is occurred, but you have already known that the case of C acylation is also there, because when you do the Claisen star condensation, that is what happens for Claisen ester condensation? You have this enolate and another ester molecule will react with this enolate. In this case, you know that C-acylation occurs. This is also a case of acylation. C-acylation occurs, but it is with ester, normal ester, but it is less. In this case, this carbonyl group is less electrophilic, and that's why it is relatively softer. I am not saying that it is soft. It is almost soft, but it is relatively softer than these sites where you have acid anhydride or acid chloride. And when you are using triplylic anhydride, it is always that the O-acylation occurs. So you have to remember that when you are using triplylic anhydride, always your oxygen group will be acylated. So this is the reaction first step. So first step, after the first step, you will get this O-acylated product. Now when you are using O3 and Me2S, you know that ozonolysis, and after that keto, or that is carbonyl groups will form. Along this double bond, two carbonyl groups will be formed, and in this case you will get a carbonyl group here, and here OTF, and another carbonyl group will be here. Now there is further reaction that after that this can go enolization, this can undergo enolization to give you this. Here you will have OTF. So here you can have this enolate, this OH and this. So enolization can either take place from this side or this side. So according to that, you can have this enolate, or you can have, sorry, in this case not enolate because base is not given, so normal enolization will occur, enol form. Okay, so either you can have this or you can have this. So these two enols can be formed from this. This is natural enolization. You know that little amount of enol is always there with equilibrium with this carbonyl form, keto form. Now you can see if this oxygen push lone pair here, attack can take place from here, but this will form 1 2 3 4 4-member ring. So this is not a favored case, but here if oxygen push lone pair, attack can take place from here, and here you can get 1 2 3 4 5 6. So 6-membered ring you can get, and this is the product you will expect. So here you will have this CO group. So this is one product you can expect. But what is the another possibility? Another possibility is that the reaction can also be take place from this keto form also. That is, this oxygen lone pair can attack here and displace this OTF group. So you will get this product. So in this case 1 2 3 4 5 6. So in this case again the 6-membered ring will be formed. So here you will have this O, and here you will have methyl group. Now this hydrogen can be eliminated to give you this product. So here you will have this. Now if you count electron, you can see this is a aromatic ring. Here you have the OMe group, here you have another OMe group. So the special stability of this compound is that you can see here you have 2 electrons, here you have 2 electrons, and also here you have another 2 electrons from this oxygen, the lone pair, and this is a vacant p orbital. So this full ring is in conjugation, and also it has 2 plus 2 plus 2 6 electrons, that is 4n plus 2 electron system. So this ring also become an aromatic ring. So 2 aromatic rings are there. So this is a very stable product. You can see aromaticity is there. Now this what are the chance of these two different products? So in this reaction this will be the product and this will not be the product, because in this case also the same logic applied, that this is the case of C-alkylation versus O-alkylation, and in this case you can generate this product from this also. if this oxygen lone pair attacks here, so what you will get? You will get this, then this hydrogen can go here and you will get this product. So from this enol also you can get the same product, and from this another enol where I have written enol from this side, that will also give the same product. So basically O-acylation will again take place, because in this case also the electrophile is this group OTF, and I already told that whenever you have OTF group, that is CF3 group, and these two highly electronegative groups are there, that makes this center very much electron deficient, that is very much hard, and that's why O-acylation will be preferred over C-acylation, and you will get this product. And also the product is very much stable due to the aromaticity, but this is kinetically controlled product, and the aromaticity of this ring is less important than this preference of the hard interaction. So main cause is the hard interaction, and although and after the formation of the product is also more stable. So both factors are favoring for this particular product, so that's why you will get this product. So this problem is very important because it gives you the concept of C-acylation versus O-acylation, and I think I'm able to explain the reaction to you. And thank you for watching, and don't forget to subscribe my channel.